So, welcome to the pre-lab lecture on the redox titration. The goal today is to test the mass percent of this iron 2, I really shouldn't say solution, solid. Iron 2, it's going to come in a solid form. When we test the mass percent, we're sort of testing the purity. How are we going to test the purity of this chemical solid that has iron 2 in it? Notice it's a cation, so there's other ions going to be present. We'll talk about that chemical formula here in a second. We're going to do a reaction. We're going to do a known reaction that's 1-to-1. Every one iron will react with one cerium. This is a redox reaction, and it makes one iron 3 and one cerium 3. During the course of this reaction, the iron 2 loses an electron. And recall from Chem 1A that when a chemical loses an electron, it has been oxidized. And then cerium gains that electron. It rips that electron away. It's more stable for the cerium 4 to have one extra electron. It's more stable for the iron to give up that electron. And so the cerium gains one electron. That means it's reduced. And again, this is a well-known reaction. We know that it occurs. We know that it occurs quickly. We know that it's 1-to-1. So we got to kind of take a lot of that as sort of a matter of fact. We got to trust in all that previous work. We could spend a lot of time trying to maybe prove a lot of that stuff, but we're going to try to use it and trust it so that we can test the purity of this iron solid. I need to do a quick recall on this from Chem 1A. There's a chance that you were pretty good at mass percent in Chem 1A, but you might be a little rusty on it. So recall, mass percent means the mass of X, one of the elements, over the total mass times 100. And you could have different mass percents. You could have a theoretical. This is from the chemical formula. This assumes 100% purity. So if you want to know the mass percent chlorine in sodium chloride, table salt, you do the mass of the X, the chloride on the top. You look at the periodic table, 35.45, divided by the total mass. So that's the sodium plus the chloride in this example, because it's just two elements. So 35.45 divided by 58.44 times 100. Sodium chloride is 60.66%. That's the theoretical. If 100% pure. If you then go do an experiment and you find that it's only 50% chloride, well, guess what? You don't have pure sodium chloride. The theoretical mass percent is a way to identify how pure a chemical is, because you could have an experimental mass percent. This is from experiment. And the way that it goes is one way or another, you find the mass of element X. It's the same chemical formula, and you find the total mass, and you multiply by 100. And again, if it's 60.66, this is evidence of two things. First, it's evidence that you actually do have table salt. It would be kind of hard to imagine another chemical that would be exactly 60.66% chloride. And two, that it was very pure. And again, they don't have to match. So today you're going to try to find the mass percent of iron in this. It's called ferrous ammonium sulfate hexahydrate. It's a long, complicated name. I don't want to spend too much time on it, but this is a good way to keep the iron 2 ion stable in a solid, and then also have it dissolve up in water pretty easily. So there might be other iron 2 compounds that are very stable, but you try to dissolve them up in water and you got to wait a day. There might be other iron 2 ions that dissolve really easy, but they're not stable. So you come back a month later and most of the iron 2 is now iron 3. And that's one thing about the experiment today, is because iron 2 gets turned to iron 3, this reaction only works with iron 2. If half of our iron 2 has already been converted to iron 3 before we get our hands on it, then our mass percent might be half. So, again, here, if the mass percent chloride was 30%, that would mean that for one reason or another, there's not as much chlorine there. Maybe it's not pure, or maybe the chloride has been converted to something else that didn't react. Let me just spend one more extra minute on this for the iron. So the iron, I think you're just going to find that it's less than 20%. I don't want to ruin too much of the calculations. You can go do the theoretical mass percent right now, right? We were looking for the mass percent iron. So iron 55.85 divided by the total mass. Add up all of the atoms. 2 sulfurs, 8 oxygens, 2 nitrogens, 8 hydrogens. And then you also have to include 6 waters. A water is 18.016, 2 hydrogens and 1 oxygen, and you got to multiply by 6. This dot right here means it's a hydrate and means that there's 6 waters that are part of the solid crystal structure. When you go and start scooping this chemical, you might see these 6 H2Os and think, well, is it kind of wet still? No, it's part of the crystal structure. These waters get adopted into the solid formation, and more waters will make it wet and won't get adopted in the crystal formation. We could talk a lot more about hydrates, but I don't want to get too derailed right here. So you got to do 6 times 18.016 and add up all those. So it's got a really big molecular weight. So let me just say that it's supposed to be 20% iron. This isn't right. It's going to be less than that. Iron 2. So this is, what we expect. This is the theoretical. This is from the chemical formula. There are 2 things that might happen. One is we might get less than 20% or less than the theoretical. I shouldn't even say a specific number here. Let's just, this is the theoretical percent, whatever you go and find it to be. Maybe pause the video, go find it now. You'll need it. If it's less than theoretical, okay, so the iron is a small percent of the solid. You're going to go weigh out a specific amount of the total compound. And then you're going to test it, and you're going to find the mass of the iron 2 from the titration. And you divide by the total mass, and you multiply by 100. If it's less than the theoretical, this means that it's impure. And that 2 reasons that it might be impure. One is other stuff is present. Salt, anything else, extra waters. We don't really know. We didn't go test for the other things. We just tested for how much iron was there and then did a quick calculation to find the mass percent iron. The other option is that maybe the iron 2 has been converted to iron 3. If half your iron 2 has been converted to iron 3, then you carry out the reaction, you're only going to find the iron 2s. And again, we're not doing an experiment for iron 3s. So we won't know why the mass percent is less than the theoretical. The other option is that perhaps the iron 2 is greater than the theoretical. For a long time, this kind of confused even me. And finally, I came up with a good reason for why that might be the case. And you might find this today. If your theoretical percent of iron 2 is more than the theoretical, what this means is that there's more iron 2 than you expect. And one explanation for that is maybe some of those waters in the hexahydrate have evaporated out. So again, going back to hydrates a little bit, when you dry it out, when you cook it, maybe you cook it at 200 and you get the hexahydrate and it has 1 color and 1 density, 1 mass percent iron. But if you warm it up or you let it sit out in air for a really long time, maybe some of those waters can start to go away. And so the only thing that we're going to know today is either it's less than the theoretical percent or more than the theoretical percent. And if it's more than the theoretical percent, that means you have more iron 2 than you expect. And again, come back over here to the pie chart. Some of it is sulfate. You could find the mass percent sulfate. Some of it is ammonium. You can find the mass percent sodium. And a good chunk of it is mass percent water. Maybe it means that the water is less than it should be. Again, we're not going to really know because we're not going to go test for how much water is there. each one of these would require a different test. You need a different test for sulfate, a different test for ammonium, a different test for water. Finally, after 3 trials of 4 tests, you would know exactly what you held on. Well, you would be pretty close. At some point, you'd always have to say, well, 0.01% is, I'm not sure, because there might be some contaminant in there. You might have to carry through some purification. So an explanation for this is that maybe some of the water evaporated. So when you go and you weigh out 100 grams, you thought you were getting a certain amount of water, but you got a lot less of that water. So that meant you got more iron 2 than you expected, and the theoretical mass percent is higher, or sorry, the experimental mass percent iron is higher than the theoretical. Okay, so we got the reaction, we got our goal, we talked a little bit about mass percent, we talked about what theoretical compared to the experimental. We're going to carry out a titration today. We're going to put the cerium, we're going to know the exact molarity. It'll say on a bottle in the back of the room, and it'll be important that you write that down and use it in all of your calculations. I think that it's pretty close to 0.1. Let's pretend that it's exactly 0.01000 molar. It might not be. You might, again, look at the bottle and see what it says. The thing that you put in the burette, and I'll show you how to work with a burette here in a second, we know the exact molarity. So you know molarity, and we will also know the volume that you add, because the burette is really good at reading volumes. Down here is 0, up here at the top is 50. So if it starts at 50, oh, sorry, that's backwards. Sorry about that. Down here is 50, up here is 0. So you always want to start with it full and reading 0. And then if, say you drain down to 10.11 milliliters, that's how much of the cerium you've added to the beaker. So that's how you know the volume that you've added at any point in time. Then the iron down here, we're going to make a certain solution of iron. We're going to go for around 0.102 molar. You might weigh a little bit more, a little bit less than you need for that. So it might be 0.100 molar, or it might be 0.105 molar. That'll be fine. This is sort of your target. This is a weird concept in chemistry, but you have to kind of start the experiment somewhere. Our goal is to find the mass percent iron. We need to dissolve up some of it to carry the reaction out. We need to know how much to dissolve. And so the experiment has said, hey, let's go for this target of 0.102. As soon as we weigh it out, it's going to be really hard to get exactly 0.102. Just write down whatever the scale is saying, and don't spend 20 minutes there trying to get an extra little granule either on or off the weigh paper. It's not really worth your time. So it'll be okay if it's 0.105. Again, you write the number that's on the scale, and then you kind of back calculate, oh, I was going for 0.102, but I actually ended up making 0.105. This is ideal. This is 0.105 molarity ideally. But again, we're going to test it and see how close to this 0.105 molar it actually is. So it's kind of a weird thing, because you weigh out a certain amount, you could do the calculation, but when you do that calculation, when you go molarity to moles to grams, that's assuming 100% pure. And it's not, right? The whole goal is to see how pure it is. So as soon as you dissolve it up, you kind of forget what the molarity is. And you're going to use the titration data to see what the molarity is. I'll show you that right now. So here you're going to know the volume, because we're going to put from a pipette exactly 25 mils of the iron in here. And here, let me steal this reaction one more time. Again, this was something is called solution stoichiometry, and you did it in Chem 1A. You might be a little bit rusty. So let's say that our cerium is 0.100 molarity. Let's say to get the equivalence point, I ended up measuring 25.75 milliliters, and the iron, I put in exactly 25 milliliters. How do you then know the molarity? Some people are going to be tempted to say, well, I know the molarity. I measured it out. This is, again, assuming 100% pure. We're testing the purity, so we can't make that assumption. Oops. So you got to actually go from the data that you know to find the molarity. So look, we know the reaction is 1-to-1. We know more about the cerium. We're going to use this equation all semester. You might get it tattooed to your forearm so that you know it. Molarity equals moles divided by liters. Here, we know more about the cerium. We know that the cerium is 0.100 molar, and we know that we use 25.75 milliliters, but molarity is per liter. So we go 1, 2, 3. This is 0.02575. So to find the moles, we do molarity times liters. 0.1 times 0.02575. No surprises, it moves the decimal point over 1. You got 0.002575 moles. A lot of times in labs, you're working with pretty small numbers of moles. You'd have to use 140.1 grams of cerium to get exactly a mole. So we're not using nearly that much. It's pretty expensive. Here's an important part. We'll go back and talk about the titration here in a second and the data that you'll collect. But the whole idea here is at the end point, the moles are equal. There's 1-to-1. So at one particular place in the titration, which is what we're trying to find, the moles are equal. So the moles of iron are also 0.002575 moles at that one particular place. But because the iron was in the beaker and came from 25 milliliters, the iron actually doesn't change. The analyte doesn't change the moles. So this is how much was in there. The thing that's changing in the cerium, because you had a little bit from the burette, then you had a little bit more, then you get to the endpoint, moles are equal, then you go past the endpoint. But now look, you have moles of iron and volume. Moles and volume. Now you know the molarity. So we're going to use the molarity equation one more time. 0.002575 divided by 0.025 0.103 molar. So I'm using these, the volume, moles to get the molarity. I got 0.1030 molar. Remember, my target based on my original target was 0.102, but maybe when I weighed it out, I got a little bit more of the solid than I wanted. So this 0.105 was how much I was expecting based on the grams that I used. And then from the experiment, from the titration data, you're going to use this calculation right here. You get 0.103. This is the experimental. And notice that this is less than the 0.105. That means we're in the first scenario. It's impure. There's other stuff present, and maybe, there's no way to know, some of the iron 2 had already been converted to iron 3 and it didn't react. Okay, so those are the sort of the theoretical things. We could go on for hours and hours on titrations. Here's what the data is going to collect. You're going to use LabQuest, plug in an ORP sensor. You're going to start with a certain, this is the ORP reading. You'll start with a certain reading. You'll add a little bit of cerium through the burette, and the reading will go down a little bit. And then it will get really steep and decrease. And then it'll flatten out again. Between these two sort of flat regions, right in the middle, is the equivalence point. That's when the moles of analyte equal the moles of titrate. That's when the moles of iron equal the moles of cerium. So our whole goal today is to just find this one equivalence point. And you'll have to, again, add it kind of slow, add the cerium slow, collect a data point. The more data you collect in this steep region, the better. Okay, so before you come to class, you might want to think about this. How much ferrous ammonium sulfate hexahydrate, again, here's the chemical formula, do you need to make 100 mils of 0.102 molar? And when you go to the scale, you might not be able to weigh out that exact amount, and that's okay. Again, write down whatever amount you used. This is your target, but then your experiment, this is from the mass might be a little bit higher. I wrote that maybe I got a little bit extra, and so I wrote 0.105 molar. Then you have a different experiment. This is from the titration data, and we saw that that was 0.103 when I made up that data. So you want to figure this out. I don't want to ruin the calculation for you, but I want you to check with me when you come into lab. You again, you're using the molarity equation. Molarity equals moles over liter. We know the liters, 0.1. We know our target molarity, 0.102. Rearrange for moles, and then moles to grams. You have to add up all of these to get the molecular weight. Okay. These are the things that you're going to need to go get. There's going to be a lab quest here. Yeah. Here's the lab quest. There's a little button on the top, and you can turn that on, and it turns on. And then you will need an ORP sensor. These will probably be in the hoods. You open those up, and there's actually two different ways to connect it. The easiest way is to just plug it in. There's a little USB port here, and so you just plug it in, and it should just pop up and say, hey, I'm connected. It says pH. The lab quest is kind of confused. If you got a red one and it says ORP, it's an ORP sensor. Lab, it'll work. It just says, I think this is a pH meter, and it's not. pH 17 would be outrageous. And now you're sort of ready to dig into the lab manual and go through the steps here. You're going to have to switch the mode. So there's 3 screens up here that are going to come in handy. Starting over on the, wow, the first one is way over here on the left. It's the main page. It's the meter page. You could click on this. You might have to calibrate. We're not going to do that. You might have to set it up. That happens with other sensors. And then up here in mode, you're going to switch to events with entry. So you click down on this little arrow, and the second one is events with entry, because you need to tell LabQuest every volume that you add. Let me actually just do it. So mode, events with entry, and then you could just leave it like this, or you could say, oh, the volume and then the milliliters, and you hit OK. And then you come over to the second tab up here. This is the data that you've collected. And then the third one shows the same, is the XY tab, and it shows the data in columns. It doesn't show anything yet because we haven't collected anything yet. If we were ready to start collecting data, I would hit this play button down here, and then I would hit keep. You're going to keep your first data point. Every time you hit keep, you're going to have to type in the volume, and your first volume will be 0. So you can just type in 0 or 0.00. And now you'd be ready to start the titration. You add a little bit of cerium. You'd wait for it to stabilize a little bit. Don't wait minutes and minutes and minutes. Don't wait for the last sig fig to stabilize. You hit, because that's where the error is. Then you hit keep. You add a little bit more, wait for it to stabilize, hit keep, so on and so forth. So that's a little bit on the lab quest. You probably have questions, and that'll be fine. Things might not work out the way that you're supposed to. Hopefully the instructions get most of us there. Again, just turn it on, connect it, switch to events with entry, and hit play, then hit keep, and you're collecting data. Here is a 100 ml volumetric flask. There, 100 mils. There's a white line right here. So you're going to put your solid in, whatever you figured out from your calculation. And again, maybe you should verify with me. You're going to put that solid in here, and then you're going to add water. You probably want to add just a little bit of water and stir it really good. Then add a little bit more water, stir it really good. Don't fill it up right away, because then it becomes really hard to mix. You have this like concrete stuck to the bottom and no space to mix it. So just add a little bit, mix it up really good, add a little bit more, mix it up a little bit more. Now it's all dissolved. Now you want to add right to the line, and you might want to use your dropper to fill it in, because if you go above that line, you got to start over. You got to rinse this out. It's okay if it starts wet. You're adding a bunch of water anyway. You want to rinse it out really, really good. You don't want any of those iron atoms left over. And then you have to go reweigh it, write down that number, add it, add water, mix it up, add more water, mix it up, add more, mix it up till it's completely mixed. Then you want to add water so the meniscus is right on the line. You want to get your eye level. You don't want to tell a meniscus from down here or up here. Got to be eye level, adding drops, get the meniscus right on the line. Once it's on that line, it's now really important to be really, really well mixed. We got some parafilm in the lab. This is a really cool material, kind of waxy. It's very hydrophobic. You can use some scissors. You cut off a little bit. It's got some preset lines here. You just need a little square of it. And you take off the paper. The paper's trash. This is the parafilm. It's very stretchy. And then eventually you overstretch it. But it's really good for mixing solutions. So you take the paper off, throw that away. Then you kind of stretch it over the top. And you can put your thumb on it. And now you got a good barrier. And you can invert it and shake it, mix it around like this. And then you will pour it off into a beaker. And you might even want to parafilm that beaker. It's kind of a good idea so that it doesn't evaporate as you're sitting there. Now you're ready to pipette exactly. This is a way to make a very precise volume, right? Because this is 100 mils, probably with 4 sig figs. It says plus or minus 0.08 milliliters. So actually it's like 5 seconds. So this is the pipette. There's another line here. This helps us measure exactly, this one's for 25 mils from one container to another. And we're going to make 100 mils. So that's enough for probably only 3. And you want to do 3 trials today. So you pour it off into a beaker. You want to first rinse your pipette. So imagine I got a little beaker right here. This is a pipette aid. Put it over the top. I like to hold my pipette with my left hand near the top. You kind of want your fingers near the very top because you want to be able to use your thumb like this. So then you got the pipette aid. I hold that in my right hand. I can't remember what I just said. So sorry, you hold your pipette in your non-dominant hand. You hold the pipette aid because you need some dexterity with your thumb over here with your dominant hand. You put that over the top and you just kind of gently put them together. You don't have to crank or turn. There's no threads here. I've seen people do some crazy things here. This is glass. You can break it. So you just kind of gently insert it. That's it. And then you put it in your solution and you pull up a little. So when I dial up here, the plunger comes up and it sucks the liquid up into the pipette. You probably only want to pull up to about here to do a rinse. And then you pull the top off, cover it with your thumb. And you want to roll the liquid around, cover every surface up to the line. So roll it all around really good and then dump it out. You've now rinsed the pipette. It's now ready to deliver your exact solution to a clean, dry beaker. Actually, it doesn't need to be dry. You're going to add a bunch of water to it anyway. So a clean beaker. And this is a really good way to start. You might want to rinse everything, all your beakers with DI water. It'll be okay. This part you want to rinse with your iron solution. Now you're ready. You've rinsed it once, could rinse it twice. Definitely don't use a whole 25 mils to rinse. Then you won't have enough to do your 3 trials. So that's why you only pull up a little bit to do a rinse. Now you put the plunger back in, you pull it up, you pull the liquid. You want to pull the liquid up slightly above. And what you'll notice when you're pulling up on this is it'll go pretty fast through the thin part, and then it'll go really slow through the bulb. And then once it gets to the top here, it'll go fast again. So I've seen people way over crank near the top, and then all of a sudden it shoots up into the pipette. You don't want liquid up in the pipette. So you gotta be kind of careful here. It's going slow. Yeah, you're cranking it, and then it's getting up here. Maybe you want to slow it down a little. You could actually push it back down and you're like, oh, okay, I don't have any more pressure. And then you pull up slowly. You want to go a little bit above it, and then you pull the aid off and cover it with your thumb. And in that instant, it will drop down a little bit. So you got to be kind of fast. And this is why it's important to have your hand near the top. Because if you're down here and you pull it off and set it down, get your finger up there, it's drained below the line. So have it near the top, pull it off, put your thumb over. It's a little bit of the line. This next part, it takes a little bit of practice. You might want to practice. What I like to do is I'll hold it over the beaker that I'm measuring in. I need to get the meniscus right on this line. And what I do is I kind of twist it. I'm kind of over exaggerating. I don't twist it like this, but you twist it. And when you're slowly twisting it, it will dial down the liquid straight to the line. Slowly. If you try to get to the line by just lifting your thumb, it'll be, oh, too much. And you got to pull some more back in. So if you slowly twist it with your thumb on there, you'll find that just twisting it in just the right way will slowly dial it down. Get it right on the meniscus. Then you got to look in here and make sure there's no air bubbles. If there's an air bubble here, bad news, you got to start over. You got to drain, get that air bubble out, fill it back up. It has to be no air bubbles here. Get your thumb on it, right at the meniscus, no air bubbles. Then you can put it over your beaker for trial 1, and you just take your thumb off and let it drain by gravity. Don't get the pipette aid back on there and try to force it through. It'll take a minute. It's got to drain by gravity. Once it gets down to about here, you will notice that the last drop stays in the tip, and it's by design. And it feels weird, but these are called to deliver. And what they do is they deliver exactly 25 milliliters. And there'll be some droplets coated on the inside here. But again, that's part of it. So when you pulled up to here, you've actually pulled in a little bit more than 25. A couple extra drops stay adhered to the surface. And that includes the last drop here. So you don't need to blow out any. That will be more than 25. You don't need to shake it so hard to get that last little drop out of the tip. If there's a hanging drop, yeah, kind of shake that one out. But the drop in the tip, leave that one. That's how you use a pipette. That's how you get exactly 25 mils into your beaker for trial 1. Whenever you're not using this, these are round. These will roll off the bench, fall onto the floor, and break. Clamp it into your burette stand. Can you see my burette stand here? It doesn't really matter above or below, but this is just the safest place for a burette that's not in your hands. Sorry, a pipette. That's a pipette. This one's the burette. This is where the cerium's going to go. Again, it's 0 at the top, 50 at the bottom, because it's not telling you how much it's holding. It's telling you how much you delivered, starting probably from 0. Same thing here. You want to rinse it. And I think that the cerium comes in a very acidic solution with sulfuric acid. So you got your funnel here. You pour the sulfuric acid, the cerium with the sulfuric acid in a little bit. Again, you want to rinse it. So you add 5 to 10 mils, no more than 10 mils. 10 mils is a good rinse. Oh, I should talk about the bottom too. This down here at the bottom is called a stopcock. It's a piece of Teflon. It's got a hole through the middle of it. When the handle is up and down like this, when it's parallel, when it's vertical and parallel to the burette, the hole is open. So if I started to fill this up and I was being really careful and I was looking up here, it would go straight through and be pouring all over my lap. When you fill this up, you want it to be closed. And it's closed when it's horizontal, parallel to the ground. Now I can be sure I'm going to start filling it up. Only do a little bit at first. I got my funnel in there. You got 10 mils. Take the funnel out. Go over to you should have one of your biggest beakers should be a waste beaker. Put that in the back middle of your bench. And you want to rinse this. So leave it closed, turn it on its side, and rotate it, spin it. And you want to coat the whole surface. And this does have a color, so you can actually see it when it's coating every single surface. And you actually also want to rinse the tip too. So then turn it back over, rinse the tip, spin the stopcock around, rinse every single surface. Then you can pour the rest out the top into your beaker. You might even rinse this one twice because a lot of surface area. We don't know what people use this for last. So you rinsed it twice. You have extra cerium, so that one's better to do a couple more rinses. And again, you close it, you put the funnel on, you fill it all the way up to 0. Probably, again, it's easier to fill it up beyond 0. Get this over your waist and then slowly open it to get the meniscus right on the 0. Again, you want to make sure there's no bubbles here. If there's a bubble in the tip or in here, open it up, let that bubble go just straight into waste, close it up, and then fill it back up to 0. Hopefully you don't need to drain the whole thing. Sometimes a bubble will get kind of stuck there and you open it up and you might have to shake it down over your waist to get the solution to push the bubble out. Whenever you're reading the burette, read it to 2 decimal points. So that is 0.00. If it was right on the 10 milliliter line, call it 10.00. If it's right on the line after 18, call it 18.10. If it's between 18.5 and 18.6, and it looks like it's right in the middle, call it 18.55. You always have to estimate the meniscus between the two lines. And this will take a little bit of trick, and it hurts our eyes and heads a little bit, but you have to be parallel to the meniscus. And you're trying to estimate between the two lines. You break it up into 10 spaces, call it 18.51, 18.55, 18.59, whatever. You're estimating the hundredths place. And you have to do that every time you get a volume measurement. For this one, for titrations, we know that near the before the equivalence point and after the equivalence point we're nowhere near the equivalence point, and we really only want that one. So you might just open it up to like 3 milliliters. I see that this pre-lab is getting a little bit long, but I'm going to try to give you one last tip on how to get good data, but not spend an hour on every single titration. So you're going to start up here with your ORP reading. Your first one, you don't really know where the equivalence point is. So this is the ORP reading. And this is the volume. It's designed to have the equivalence point at exactly 25 milliliters. But again, it could be less, it could be more. This probably means that at least the first 15, there shouldn't be any surprises. So your first one, you might do like every 5 mils and just set it exact. So do 5.00, 5.00, then 10.00, then 15.00. Then you might slow down a little bit. And then you might do every 1 milliliter. So you do 16, 17. Now you notice it's starting to get really, really steep. 18, 19, 20. Now it's getting really, really steep. And you might, I'm saying slow down, but what I mean is you add smaller and smaller volumes. So 16, 17, 18, 19, 20. It's getting really, really steep. Now you might get to the place where you're adding like half a mil or a couple drops. In theory, every 1 drop is about 0.05 milliliters. About 20 drops is 1 milliliter. If you just spin, you can't really see it. If you just spin the stopcock 180 degrees as fast as you can, you'll get about 1 or 2 drops. Also notice that the stopcock, it's not necessarily either open or closed. You can find kind of a gray area where it's slowly dripping. If you have it wide open, 5 milliliters will go pretty quick. So you might want to find like some middle area where it's doing drop wise. And so you get a little bit more control. And on your first one, you might find that you missed the equivalence point. You were still adding a milliliter and all of a sudden it's down here. And then you're still doing a milliliter and it's flattening out again. Now you could go back to 5 milliliters. So you could go exactly 30.0, 35, 40. Once it's really, really flat, you don't need to go all the way to 50. You could if you wanted to, but these two right here, it was over. So I kind of just used these last 5 mils and didn't get any extra information. LabQuest will tell you where the equivalence point is, but it will point to this one right here, because it's looking for the smallest increase in volume with the biggest increase in ORP reading. And this was it. It was 1 milliliter and it was a huge drop. So it's going to call this the end point or equivalence point, and you'll just have to use that one. But hopefully you'll come to appreciate that this isn't the most accurate endpoint. It just sort of happens that the first one is usually your least accurate because you don't know exactly where the equivalence point is, because you were just reading this data up here. But your second one, now you have a really good idea, because your second one, you've added exactly 25 mils with the pipette into the second beaker. So now you're going to go through and hopefully get a lot better equivalence point. Again, we're not going to expect the equivalence point in the first 15. So maybe you go 5, 10, 15. Now you go slow for 1 or 2. But now you say, and sorry, these should actually be right on top of the last ones in theory, because everything's exactly the same. But now you're going to slow down a little bit. Now you're going to go dropwise, and you're going to get a lot more data points. This is what a good titration looks like. A lot of equivalence points through the steep region. And then once it flattens out, again, go 5 mils at a time. Now your equivalence point will be a lot more accurate. And maybe the equivalence point on your second one will be here. So you might make a note in your lab manual. On my first one, I missed it. There's a huge gap. I added too much. I missed the equivalence point. The volume, yeah, I can do the calculations, but it's not as accurate as it could be. But the second one, I was much more careful. I was adding dropwise near the equivalence point. I got a lot more data in the steep region. You're going to use this one equivalence point. Maybe that comes out to exactly, 21.79 milliliters. Read your burette to the hundredths place, especially in the middle when you're going dropwise. And then hopefully, if you did your second one really carefully, your third one will also be super careful. Don't go dropwise at the very beginning, especially on your second or third trial. You know the equivalence point is around 21.79 milliliters. There is no point to go dropwise in the first 15 milliliters. Okay, that would kind of be a waste of time. Yeah, your titration curve will look really, really good, but we only use one number, this one volume at the equivalence point to do all of your calculations. None of the other ones we use. They're just there to help us find this one, because you can't just go through a titration and just get one. How do you know that's the equivalence point? You don't. So the other ones are there to help you find this one, but you don't need a lot in the flat regions. So especially on the second or third trial, start slowing down, 5, 8 milliliters before your first equivalence point. Okay. So this has been a pretty long pre-lab. It's your first time in lab, most likely. And we talked about the lab quest. You're going to have to set up your ring stand with your burette directed into your beaker. You can use your volumetric flask, the pipette aid. Oh, there's going to be this black clamp that fits onto the ring stand that will hold the ORP sensor. Oh yeah, I should actually talk about that too. So the ORP sensor is very sensitive at the bottom. It's stored in this. It's a buffer solution. So you have to kind of just gently pull it out. I hope I don't drip all over my computer stuff. There's a thin glass membrane down there at the bottom. And there's a chance that this solution, this one, is really nasty. I'm going to ask you to rinse these out, but then make sure we put in a buffer solution to fill it back up. So you're putting in fresh buffer, and you want to rinse it really, really good with water. So you're going to get your little wash bottle and kind of hose it down. And then you'll get one of those Kim wipes. They're in little green boxes in the lab, and you kind of dry off the outside. You kind of just pull straight down. Don't get in there and try and touch the glass membrane with the paper. That doesn't really work that well. Never touch that glass membrane. They're too easy to break. Hose it down, dry it off. Then you could put it in your the holder. There's these black clamps in lab, and you could put the ORP sensor through it. The last little hole fits it perfectly. And then over the bottom, so there's this black with a hole. So the ORP goes in through there and it hangs out the bottom. You'll have to raise or lower it to get the ORP sensor into your beaker. But over this bottom, we're going to put a little stir device. So it's kind of like a sleeve. And it's also black, but I'll just show it in a different color. And it's got a magnet that spins off the bottom. And this way the two don't touch. And then this whole thing will go in the beaker, and you want to make sure that the magnet can move freely. So you don't want to pinch it up against the side or the bottom, but you want to get this as low as possible into the beaker, because we need to have the sensor itself submerged by the solution. So you're going to put your 25 mils of iron in here from the pipette, and it won't be enough. And so what you're going to do then is you're going to add a bunch of water. And at first that feels kind of weird. You just carefully measured 25 mils of iron. And now you're going to add a ton of water. Don't worry about that. We don't use this water in the calculation. And as long as that water doesn't have iron 2, the amount of iron 2 in the 25 mils doesn't change. And that's what we're finding. So you just add enough water to get the sensor submerged. Now you're ready to hit keep on your first data point. Then you set the burette up so that it's sending in the cerium. Add, again, 5 mils to start. Let it mix for a minute. When you look on the LabQuest, the sensor reading, it will slowly be dropping. It'll go 16.76, 16.8, 69, 16.61. Once it slows down a little bit, 5.9, then 16.58, hit keep. It I call this drift, and there's a lot of drift in it. And you could spend 90 minutes on your first trial. So don't worry so much about the last sig fig. Once for about a minute, it's kind of staying pretty constant in the 10th place. Hit keep and move on and get more data. Don't hit keep as soon as the solution goes in there. You do have to wait for a minute for this cerium to mix in and react and equilibrate. Okay, I think that's good on a pre-lab lecture. Probably I forgot something, but at least you'll be able to get started and hopefully collect some really good data. Again, I'm asking everybody to do 3 trials. Move this report sheet over to your lab manual. You can already calculate the theoretical percent iron. What we're doing in lab is calculating an experimental percent. And then percent error is always calculated the same way. It's your actual minus your experimental. So actual is what we call the theoretical, it's from the mass percent. And the experimental, this was the grams of iron that you found over the grams of total compound times 100. And then over the actual, and the top part is absolute value. So we don't care if it's less or more. You just omit the negative sign. Divided by the actual times 100. And for percent error, especially if this is your first lab in person, less than 5%. Actually, this experiment, it doesn't say anything about you. It said it's talking about the purity of the compound. So percent error, less than 5% error, that's pretty pure. We would use that one. If it's less than 1% pure, less than 1% error, then we would say it's really pure. If it's less than 0.1% air, then it's essentially just that compound. 99.9 is a lot of times the most pure that you can get a particular something. How will you know if, or how will we know if you didn't collect the best data? It will be if the volume of cerium in your 3 trials is very different. If you got 25.89 on the first one and 23.14 and then 20.67, these are too far apart. Everything else is the same. The volume of the iron, this is from the pipette. If you use the pipette correctly, you put in 25.00 every time. And, oops, I got this one line down. And so the volume of the cerium to get to the equivalence point should have been the exact same. And this is, 2.7 different. And this is another 2.5 off. We're not sure which of these is right. None of them are that close to each other. So what does good data look like? Really good data means that all 3, or at least the last 2, are very close to each other. So if your first one's off, again, don't even sweat it. You don't know where the equivalence point is. You might have missed it. That's fine. But then if your next 2 are really close to each other, they agree to 3 sig figs, you can be pretty confident that you're finding the experimental mass percent of that solution.